In the previous session, we studied geometric representation of signal. It's a way of representing any set of m energy signal as linear combination of orthonormal basis function, which is given by this equation. So here the term Sij represent this equation. It is nothing but integrating finite duration signal over the time duration t by multiplying that with the orthonormal basis function. One of the property of orthonormal basis function is as shown here. If we have real valued basis function, if it forms orthonormal set when it satisfies this equation, that is integral over the duration 0 to t phi I of t phi j of t into dt yields 1 for I is equal to j. For I not equal to j, it yields 0. So based on this equation, we have written the block diagram of synthesizer and the block diagram of analyzer. In synthesizer, Si of t, that is finite duration energy signal, is generated from n elements of vector when it is multiplied by orthonormal basis function as shown. Similarly, if I have Si of t, finite duration energy signal, if it is multiplied with orthonormal basis function and passed through integrator, we are able to get the vector values here. So this is called analyzer. So based on this, let us try to analyze geometric representation of signal. Once again, these equations are written, that is finite duration energy signal is represented by linear combination of orthonormal basis function, where Sij is given by this equation and orthonormal basis function follows this property. So let us consider the geometric representation of signal for n is equal to 2 and m is equal to 3. What is here n and m stands for? Here n is equal to 2 means the orthonormal basis function are 2 here, phi 1 and phi 2. M is equal to 3 means there are 3 signal S1, S2 and S3. Therefore, the real value of these signals can be written like this. S1 is given by S11, S12. Here you can able to see the coordinates. S1 is equal to here S11, which is having the value 3, and S12, that is 1. Similarly, S2 here is nothing but the vector that is given by S21 and S22. Similarly, S3 is nothing but represented by the vector distance S31 and S32. All these coordinates are as shown: 3, 1, 1, 3 and 2 minus 2. So here there are 3 signal S1, S2, S3, that is the vector value of 3 signals. Therefore, M is equal to 3 we have taken. 2 basis functions are there, phi 1 and phi 2. That is why here n is equal to 2 we have considered. Now, signal S1 of t, the first signal, is represented by the linear combination of basis function, orthonormal basis function like this. You take phi 1, phi 2 and S1 1 and S1 to multiply it. So we are able to get 3 phi 1 plus phi 2. In a similar way, S2 of t can be expressed in terms of orthonormal basis function as shown, and S3 of t is given by this equation. Based on this, we are going to understand Gram-Schmidt orthogonalization procedure, which can be analyzed by the following equation. So finite duration signal is given by linear combination of the vector values and basis function. So here Si of t is equal to summation j is equal to 1 to n Sij phi j of t. So what is the condition here? So the value of I is ranging from 1 to 3 up to m. That means there are m signal, and the value of j is equal to 1 to 3 up to n. What is the one more condition? N should be always less than equal to m here. So what is the expression for this real value Sij? So from our previous discussion, the real value of this complex number is given by integrating Si of t, that is finite duration signal, over the time duration t along with the orthonormal function phi j of t. So at the same time, this basis function follows the property of orthonormal set. That is, when you integrate the orthonormal basis function phi I of t, phi j of t over t duration, you are going to get value 1 if I is equal to j, and 0 if I is not equal to j. So with this, let us try to write the Gram-Schmidt orthogonalization procedure. So let us consider the basic equation here. Si of t, that is nothing but the finite duration signal, is represented by linear combination of the orthonormal basis function summation j is equal to 1 to n Sij into phi j of t. Now let us call this equation as the first equation. So now we are going to write a set of equation that is given by S1 of t is equal to S11 phi 1 of t plus S12 phi 2 of t. Similarly, the last term I am going to write here is S1n phi n of t. So here I is changing from 1 to n in this direction, whereas j is varying from 1 to n in this direction. So I am going to write here j varies from 1 to 3 up to n here in this direction, and I varies from 1 to 3 up to m in this direction. That means there are m signals and n orthonormal basis function. So similarly, the second equation we are going to write S2 of t is equal to S21 into phi 1 of t plus S22 into phi 2 of t, and the last term in this second equation will be S2n into phi n of t. Similarly, the last equation we are going to write here is the mth signal, finite energy signal Sm of t, that is equal to Sm1 phi 1 of t plus Sm2 phi 2 of t, and the last term in this last equation will be Sm into phi n of t. So let us call this equation as 2.1, 2.2. Similarly, this is 2.n, that is the last equation. So now we are going to write the expression for signals, that is m signals, in terms of orthonormal basis function. So in step 1, we are going to consider the value of I is equal to 1 and j is equal to 1 only. So the equation 1 we are going to consider now. So that is nothing but finite duration energy signal is given by linear combination of the orthonormal basis function using this equation j is equal to 1 to n. So when I consider I is equal to 1, j is equal to 1, this equation reduces to S1 of t, that is equal to S11 into phi 1 of t. So here, in order to cancel phi 1 of t, we are going to square this equation 2 and integrate over t. Therefore, squaring both sides and integrating over t, integrating over t. Therefore, equation 2 reduces to integral 0 to t s1 square t into dt, that is equal to integration 0 to t s11 into phi 1 of t square. Here s1 square, s11 square into phi 1 square t into dt. So by the property of orthonormal set basis function, here we found that I is equal to j. Therefore, this yields phi 1 square t into dt over t duration yields the value 1. Therefore, the value of S11 we can write here as square root of integral 0 to t S1 square of t into dt. So once S11 is available, then we can write S1 of t in terms of first orthonormal basis function, that is phi 1 of t is given by S1 of t by square root of S11, that is nothing but here integral 0 to t S1 square t into dt. So this is the first step, expressing the first signal S1 of t in terms of orthonormal basis function. So now let us consider step 2. In step 2, I am going to consider I is equal to 2 and j varies from 1 to 2. So again, let us write the equation, fundamental equation. Finite energy signal is represented by linear combination of orthonormal basis function, that is by this equation. So let us consider here I is equal to 2 and j is equal to 1 and 2 in this equation, that is the first equation we considered. Therefore, we are going to write here S2 of t is equal to S21 into phi 1 of t plus S22 into phi 2 of t. So this phi 1 of t we know from previous step. From previous step we calculated that what is phi 1 of t. Similarly, we know what is S2 of t. This we know. These two terms we know. We don't know S21 and we don't know what is S22 and what is S phi 2 of t also we don't know. Therefore, we are going to consider here an intermediate function that g2 of t we are going to consider by this expression S22 into phi 2 of t. So in order to get expression for S21 here, multiply this equation 2 both sides by phi 1 of t. Therefore, multiplying equation 2 both sides by phi 1 of t and integrating over t 0 to t S2 of t into phi 1 of t dt, that is equal to integral 0 to t S21 phi 1 of t into phi 1 of t into dt plus integral 0 to t S22 into phi 2 of t into phi 1 of t dt. Since I is not equal to j, this term cancel because this yields 0. Here we are going to consider the orthonormal basis set property. Since I is equal to j, this integration over t duration yields 1. Therefore, we are going to get S21 is equal to 0 to t S2 of t into phi 1 of t into dt. The shortcut method in order to remember S21 is this 2 stands for the second finite duration signal S2 of t and this subscript 1 stands for first orthonormal basis function we have obtained from the previous step. Once S21 is available, now we can calculate S22. So from this expression, whatever I am highlighting here, we can write expression for S22 by squaring the equation both sides and integrating over t. Therefore, S22 is given by square root of integral 0 to t g2 square t into dt. What is g2 of t here? G2 of t is nothing but S2 of t minus S21 into phi 1 of t. Here, this is G2 of t. So, we have to find G2 of t in order to calculate S22. Therefore, we have written here G2 of t like this. So what is the final expression for second orthonormal basis function? Phi 2 of t is equal to G2 of t divided by square root of integral 0 to t G2 square t into dt. This is the second step. In a similar way, we can write the third steps, that is step 3, by considering I is equal to 3 and j is equal to 1, 2 and 3. Therefore, I can write the equation S3 of t is equal to S31 into phi 1 of t plus S32 into phi 2 of t plus S33 into phi 3 of t. So which are the terms we know? So S3 of t we know, phi 1 of t we know, phi 2 of t we know, but these terms we don't know. S31, S32, S33 and phi 3t. So let us consider this expression. S3353 of t is nothing but a intermediate term G3 of t. So in order to find S31, S32 and S33, from our previous discussion, S31 is nothing but directly we can write here S3 of t into phi 1 of t into dt. Similarly, S32 is given by integral 0 to t S3 of t into phi 2 of t into dt. Square G3 of t both sides and integrate over t. So we are going to get S33 is equal to square root of integral 0 to t G3 square t into dt. What is G3 of t? G3 of t is given by the expression S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t. So this type of process continues in step 4, 5, 6 and 7. So based on this, the general expression one can write for the Gram-Schmidt orthogonalization procedure. So this is how we are able to find the orthonormal basis function. So we are now able to write the expression for orthonormal basis function, that is phi 3 of t. So phi 3 of t is equal to here G3 of t by square root of what is S33? 0 to t, it is G3 square of t into dt. So let us summarize the equations that we have derived. So S1 of t can be represented in terms of the first orthonormal basis function. Phi 1 of t is given by S1 of t by S11. What is S11? It is S1 of t by square root of integral 0 to t S1 square t into dt. So this is how we are going to obtain first orthonormal basis function for first signal. So now the second signal S2 of t, where phi 2 of t is given by phi 2 of t is given by G2 of t divided by square root of integral 0 to t G2 square t into dt. What is G2 of t? G2 of t is nothing but S22 into phi 2 of t. So what is the expression for G2 of t in terms of S21 and phi 1 of t? Therefore, G2 of t is equal to S21 S2 of t minus S21 into phi 1 of t. And S3 of t, what is the expression for phi 3 of t? That is third orthonormal basis function. It is G3 of t divided by square root of integral 0 to t G3 square t into dt. So what is G3 of t? G3 of t is nothing but S33 into phi 3 of t. So what is G3 of t in terms of the previous signals? So G3 of t is nothing but S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t. So here what are the expression for S21, S31, S32? The general expression here is S21 is equal to integral over 0 to t s2 of t into phi 2 of t into dt. What is the expression for s31 here? S31 is nothing but integral 0 to t s31 s3 of t into phi 1 of t into dt, and s32 is given by integral 0 to t s3 of t into phi 2 of t into dt. We already know what is S33. S33 is nothing but square root of 0 to t g3 square t dt. So this is how the signals, finite duration energy signals, are represented by orthonormal basis function. So this procedure is known as Gram-Schmidt orthogonalization procedure. We'll solve some problem in the next session.